As of now, we have looked at some of the history and present status of quantum computation and information. So there are few overreaching questions such as what is the future, what it can offer to science and technology, how it benefit to the fields like computer science, information theory and physics, debate on spooky action at a distance, and what are some key open problems. Companies, especially pharmaceutical companies, spend on an average 25% of their earnings on drug research and development. I'm talking of billions of dollars here. The average cost of data breach is $3.86 million. 50% of the organizations around the globe store their data in the cloud, and most of it being a sensitive data. What if all this time and money could be saved and redirected to better and more crucial matters? Won't our business people and ultimately the world flourish? Imagine a future where research and development investments are just a fraction of the current investments. A superbly efficient and secure system ensures that our data is kept absolutely safe. The business and the financial institution don't need to stare in the abscess to find the best investment opportunity. With just all this possible with a few clicks on our laptop. Welcome to the quantum age. What it offers to science and technology. Let's consider the four major sectors that shows the quantum advantage over the classical models. It includes finance, machine learning and artificial intelligence, cryptography, and drug discovery. The problem needed to be solved in the financial industry are complex and computation intensive. It includes numerical risk modeling and optimization problems such as portfolio optimization and credit card scoring. Its application in machine learning help in detecting anomalies like frauds, and quantum neural networks have the potential to improve the existing natural language neural networks. In cryptography, quantum computing shows up at two fronts: a challenge and a threat to the existing symmetric and asymmetric cryptography scheme, and as an alternative to the existing cryptography scheme. In the former case, Shor's algorithm can be used to crack both factorization and discrete logarithmic problem. And in the second front, quantum computing address post-quantum cryptography, an era where the cryptography schemes are quantum resistant. Quantum key distribution is used to securely exchange cryptography keys between two parties over an insecure channel. Several protocols divided in three families: the discrete variable coding, the continuous variable coding, the distributed phase reference coding. It have been developed and as can be seen on the screen. In drug discovery, we can stimulate complex systems with several parts on the computers without having to spend a ton of money in physically building a prototype. EPR Paradox. As we know that the fastest thing in the universe is light. It travels a foot in a billionth of a second. Now let's take two entangled particles and separate them by 10 feet. It will take 10 billionth of seconds to travel from one to another. So now let's get tricky. We'll measure the horizontal spin of one of the two particles and see that it is to the right. Then 5 billionth of the second later, we measure the horizontal spin of the other particle. We find that 100% of the time it is to the left. And remember that we did it so fast that not even the light could have told the second particle the outcome of the measurement of the first particle. This means that quantum information can travel faster than light. And this thing blew Einstein's mind too. So he co-authorized a paper in 1935 with his companion Boris Podolsky and Nathan Rosen that highlighted this problem. He also called this transfer of quantum information spooky action at a distance. And this was one of the reasons why Einstein did not like quantum mechanics. What do we think about this phenomenon today? Does quantum information move at speed faster than light? Yeah, it seems to. But it does not invalidate Einstein's theory of relativity as we can't control it. Some people, including Einstein, who thought that this wasn't so mysterious after all, the technical name for this more ordinary connection is called hidden variables. So lots of research happened for this, and as well as the contribution given by many scientists. So, proving this experimentally, we all end up to know that the idea that the final measurement is already determined at the end of the two particles are entangled is false. Hence, proving hidden variable is wrong and quantum mechanics is right.